today's topic is stealth web scraping techniques for open source intelligence, or otherwise known as stalking the rich and powerful. Our speakers today are Suhail Sharabi, Suhail? Yes, Suhail, and Francois Grenier. Grenier. Thank you. You can tell I'm British because I can't fucking do, like names from other places, even though I've got several of my own. Francois is a web pen tester, all the usual stuff. Suhail is an offensive security specialist with hands-on experience in red team operations and cyber exposure audits. That sounds really, really exciting. Open source techniques for, stalking the rich and famous. Take it away. Round of applause, please.
Hi everyone, and thank you all for coming and joining us today. Welcome to our talk on stealth web scraping techniques for OSINT. So today we're diving into how we can extract information from modern web environments in ways that are flexible and reliable. So before we jump into the technical parts, we're going to do some quick introductions. So I am Suhail Sharabi. I'm part of the Deloitte's Morocco Cyber Center team, and I'm based in Casablanca. I specialize in OSINT within red team operations, and with a focus on digital footprint and exposure mapping. In other words, I spend most of my time mapping the online presence of organizations and finding ways to get in. Joined today by Francois, my brilliant co-speaker, and I will just hand it over to him for his introduction.
So, hello everybody. Hello everybody. So, my name is Francois Grenier. So, I'm passionate about web security, especially client-side aspect of the web security. So I love purpose like browser fingerprinting, or for example, cross-site leaks. And I'm also an offensive security consultant.
Thank you. So before we dive in, let's take a quick look at what we will be covering today. So we'll just start with a quick introduction of the challenges we're actually facing in modern OSINT, and then we'll go through a series of techniques, of scrapping techniques and detection tricks. Then we'll wrap up with the practical takeaways you can apply to your own automation workflows. So let's set the stage. In our day-to-day red team work, our goal is very simple. It's to test real-world resilience by thinking and acting like a real attacker. That being said, we start with zero knowledge, and our mission is to uncover exactly how exposed an organization really is. So the very first step of our job is to do reconnaissance, and we have to gather information and build a detailed map of what's exposed. So this is very well known as reconnaissance. And when we do this, we deal with a lot of type of data coming from multiple sources. So the real question is, even if you find this data, which of it actually matters to us and how we can collect it quickly and at scale. And that's where automation becomes critical, and web scraping becomes one of our go-to tools. So here's the catch. Today's scrapping isn't what it was years ago. And that's why we're here, because now APIs aren't open anymore. They are gated, private, or behind logins. And even if we manage to find one, we have rate limits very fast. So many APIs require sessions, tokens, or JavaScript-generated signatures, and plus the real deal is in the initial HTML isn't rendered anymore since the modern framework render it client-side. So the HTML is basically just a skeleton, and the data loads dynamically after fetches or user action. And of course, manual browsing, that doesn't scale, it's slow and inconsistent. And all of this creates a gap between what's publicly reachable in theory and what's actually observable at practice. So if scrapping today is complicated, where do we even start? And before getting into the fancy tools and stealthy browser tricks, let's rewind a little bit to the absolute basics, which is the first thing anyone tries when they want to pull data from a site, which are their direct HTTP requests. And this is the classic just hit the endpoint approach. And when we say just hit the endpoint approach, we actually mean that. We're just going to identify a URL where our data lives, and we just send a plain HTTP or HTTPS request to fetch it. And it's the most bare bones way to scrap. You can just spin it up in seconds with Python request library or Node.js, or even just open a terminal and type a curl command. And it's considered super fast because we are skipping the whole browser. So no rendering, no JavaScript, no CSS. And we just ask the server for the data, and it sends us the HTML or the JSON directly. It's also simple because the logic is pretty straightforward. We send a request, we get the response, we parse it. But the problem with this is this technique doesn't stand a chance with modern websites. First, because we have the dynamic JavaScript rendering. And with framework like React, Angular, or Vue, the server sends you almost nothing. And the actual data is built on your browser after the page loads. And then we have the browser fingerprinting and anti-bot systems that when we send a request without a browser, we are missing a ton of little details. Like we have the elastic headers, we have the browser fingerprints, the cookies, and even the natural interactions patterns. And like for detection systems like Cloudflare, Akamai, or Datadom, they just look for those gaps. They serve you, a GS challenge or an invisible CAPTCHA and just block you outright. So bottom line, direct HTTP still works for simple stuff, but against GS-heavy sites or active anti-bot systems, we're not getting far. So we've seen why just sending HTTP requests leaves huge gaps. But here's the kicker. Detection teams don't even have to get fancy to spot us. They just ask one simple question. Are you acting like a real browser? And to answer that, they run what we can call a 3-layer test. So for instance, on the HTML layer, if you can't render the page, you fail. They might just hide a tiny image or iframe in the HTML, and if you never load it, then boom, got. And by the way, Yahoo login page does exactly this. And on the CSS layer, for real browser CSS engine, they load backgrounds, images, and fonts, and bots often skip them. So they add a CSS background image from their server, and if you don't request it, they would know. Then we have the JavaScript, and this is where it gets spicy, because a script can, inject just an image tag dynamically, and if JS is not running, then, if this JS is running, we have the image that's going to be loaded. But if it doesn't, that means that you're a bot. And we have also a bonus check, which is the no script tag, and if that's all we see, JS is off. And what's brilliant is we're not doing here any fingerprinting or any CAPTCHAs, just seeing if you loaded what every normal browser would. And if you fail, then you're marked as a bot. But here's something important to keep in mind is that some humans can also fail these tests. You can be a real human, but you can still miss all of the 3 layers in case you are, for instance, using a Tor browser in the safest mode or a privacy plugin. So these, if you want these checks, are just are not proof. They are just signals that you might be a bot. And that's where things get tricky, because if you are a bot, you can actually pass all of these tests, but it's kind of painful. Which brings us to how we can fake it like a human. So let's say you're a bot and you fail the HTML, CSS, GS detection test. This doesn't have to be the end, because in theory, you could patch the obvious gaps by adding all the standard headers, the user agent, the referrer, the whole Chrome bingo card. And you can also manage cookies or CSRF tokens correctly. And you can also introduce delays to make it sound more human. So with enough effort, you might pass the initial detection layer, but the real challenge starts when JavaScript enters the picture. Since modern websites, as we said, don't just render HTML, they generate tokens, etc. That means that you will have to replicate and reverse engineer the code and rebuild your own environments. So yes, you can try to do all of that, but at this point, you're not building it. Basically, you're just building a headless browser from scratch, and spoiler, it's going to break every time the website changes. So before we go down that path, you should ask yourself, wouldn't it be better to just run in the browser to begin with? And that's exactly where we be headed next. If pretending to be a browser is too painful, then why not just be the browser? Okay, so now let's talk about scrapping from inside the browser, and this is where user extensions come in. They are those small add-ons that they run inside your browser, and they can execute code directly in the context of any page. And they are considered powerful for scrapping and OSINT because they can see the fully rendered DOM after all JavaScript runs. They can interact with dynamic elements. They can bypass also many anti-bot systems checks by using a real browser session. And they support hybrid automation. So for instance, you're going to define a script. They're going to handle most of your work, and you step in just when needed. Like, for instance, if you have a CAPTCHA, you can just validate that and then do the automation part. And there are a lot of user script extensions like GreaseMonkey, Violent Monkey, and others. But for this presentation and for the upcoming demonstration we'll be doing, we're going to use TemperMonkey, and it's because first it's very used and the most downloaded one, and also because he's the only one that's still available on Chrome Web Store because Violent Monkey has been removed. And because it runs in a normal human-driven browser profile, and also the most important thing is that anti-bot systems don't even bother detecting it because they see it as a harmless personal automation tool rather than a scrapping engine. So, all right, before we even write a single line of scrapping logic, we gotta tell TemperMonkey where and how our script should run. And that's done in the metadata block, where you will find the multiple fields. And the four first fields, like name, namespace, version, description, those are basically fields that's going to help you be clean and more organized, especially if you have multiple scripts to manage. And then you have the @match, and this one is very important because it decides which URL is going to trigger the scripts, the user scripts. And then we have the run @, and it tells the TemperMonkey scripts when they're going to be executed. Is it on before the DOM parsing, after, or when all assets are loaded? Then, when we define the script, TemperMonkey waits for a matching page load, and then begins its multi-step injection process. So the first step is the browser tab, and when a user opens a URL, TemperMonkey hooks it into the navigation lifecycle, and it only reacts to the actual page load. It's not watching idle network traffic or AJAX calls on their own. Then we have the extension match, which is when TemperMonkey checks every installed user script against the current page's URL using the match field that we've presented earlier. And they're going to also read the run @ to see when the script will be executed, and also the sandbox to define the execution context. And if there is no match, the script is ignored silently, but if there is, it's going to be scheduled for injection at the right time. Then we have the wrapper script injection, and that moment is defined by the run @. So TemperMonkey injects a small wrapper script that runs inside an isolated execution context. It can read and change the DOM, but cannot directly access the site's JS variables unless you run it in a page context. Then we have the CSP header removal, and if the site uses a content security policy, that would block inline scripts. But TemperMonkey is going to intercept the page's responses and remove the CSP headers using web request blocking. The next step is the user script code injection, and the actual user script is added to the target page as an inline script tag, and TemperMonkey is going to expose it via generated window, letting it execute in the same scope as the site's own JavaScript. Then the last and the final step is the execution content, when TemperMonkey calls that function and your script runs with full capabilities, like reading the DOM and manipulating the DOM elements and monitoring for clicks, keystrokes, etc. Okay, so now that we've shifted scrapping into the browser using user scripts extensions, let's pause for a second and flip perspective. What if we are the ones being observed? Because browser extensions can be pretty useful, but they can actually leak a surprising amount of information. And one of the best-known examples is web accessible resources. And these resources have a access control allow origin header set to wildcard, which basically means that from our website, we can check for the presence of an extension by simply making a client-side fetch request. And another one is DOM manipulation, and here some extensions can modify the page's HTML or inject scripts directly, like for instance that's what Wapolizer does, and we can detect this with the mutation observer API or by hooking functions like post messages, often used for page extension communication. And finally, we have custom extension behaviors. In certain cases, combining these quirks with a vulnerability can expose which extensions a visitor is running, and all from the website they're going to load. Now, though, if we focus on the extension leaks from TemperMonkey scripts, we have this very specific URL on TemperMonkey, which is the installation script. And when TemperMonkey sees this, it performs a client-side redirect. If we open a pop-up to this URL and watch the behavior, we can tell instantly if TemperMonkey is installed. And the second one is if it spots a file that looks like a user script, you know, the user.js. It automatically opens its installation suggestion page, and a neat trick here is using the @icon field in the script metadata, and if we host that icon on our server, then we'll be able to get a callback the moment that page is logged, which could help us confirm that the TemperMonkey extension is installed. And finally, TemperMonkey injects scripts directly into the DOM, stripping headers, and if we hook functions commonly used in the user script, like document query selector or document title, we can catch those calls. And the stack trace will reveal TemperMonkey as the source. So to avoid hooking everything, we can just analyze the most popular functions being used and hook them. So that's what exactly we did for our proof of concept. So let's take this concept into something a bit more hands-on. And for this first demonstration, we're going to watch the TemperMonkey's injection process in real time. So our tool of choice is the mutation observer API. And for anyone who hasn't used it before, it just let us listen for changes in the DOM as they happen. So we just set up a mutation observer on the page, and it tells us, like, let me know when the moment you see a script tag appears, give me its contents. Okay, so what we did here is, we just defined a TemperMonkey user script. We pointed it to match the URL of a web page that we developed for this demonstration, which is scrapme.fun. And inside the function, we just did a console log function that we hooked on our website. So then we're just gonna save this script. And after that, we're just gonna visit the scrapme.fun. We're gonna have to reload it so that TemperMonkey can be triggered. Sometimes it takes, it doesn't detect it right away, so you just have to reload. And now that the TemperMonkey has been triggered, we can see on our dashboard detection that the mutation observer, if we see its content, we can actually get the user script that has been injected. And here we see the console log function that we've defined earlier, and that's because we hooked this. And the second detection method is using the stack trait inspection. We can see that the call here originated from TemperMonkey injected script. Okay, so this is where in the first demonstration, we were manipulating the DOM, but what if we could tell the TemperMonkey extension to tell us that it's there without actually having to need an actual execution of a user script? And that's exactly what we did in this demonstration. So we're going to take advantage of one of TemperMonkey's built-in behaviors and let the extension reveal itself through a simple browser redirect. And here's how it works. We start first by opening a pop-up with the Temper Monkey installation scripts, and for that we defined a function that's called when we click on this button. I don't know if you can see it. Oh, it was a bit too fast. So what happens here, when the pop-up is opened on the Open Redirect Vulnerable Temper Monkey URL, we're going to get redirected to our scrapme.fun website, because it's the one we have control over. And because of the destination is our domain, the same origin policy works in our favor. So we can actually read and inspect everything on that, everything on that page directly from the JavaScript. And for this third demonstration, we're going to still target the same vulnerable Temper Monkey installation URL as before, but this time, instead of redirecting the user to a website that we control, we're going to redirect them to a custom user script. And it's basically just a minimalistic script on which we've set an icon value that points to a favicon hosted on our server, scrapme server again. And when the redirect works, Temper Monkey opens its ask.html page, the one that prompts basically when a user prompts the user to install the script, and this page is automatically loads our favicon in an image tag as part of the extensions interface. So here what's going to happen is we're going to click on the second button, and then we will have will be redirected to the Temper Monkey ask.html, and we can see the Y icon that's actually hosted in our scrapme website. I'll just rewind a little bit so you can see it. So here it's called from scrapme.fun favicon.png, which can allow us, to know that this is actually a Temper Monkey extension that is installed on the target's browser. And here the detection signal isn't a visible redirect we can read, but it's a network callback from a resource load triggered inside the extension's own URL. Okay, so far we've talked about how to detect Temper Monkey, and now let's flip it. If we're using it, how we can avoid detection. And most detection methods, as we've seen, rely on hooking and stack trace inspection. So the rule number one is we have to avoid calling JavaScript functions directly from the visited page whenever possible. And Temper Monkey provides bridge functions defined inside the extension that's going to help us bypass hooked pages functions entirely. So if you need a clean and unhooked function, you can create an about blank iframe and pull the function from there and apply it to the page context, the visited page window. So you can also check if a function has been hooked by running to string on it. So if the result doesn't contain native code on the real function name, that means that it's hooked. And just a quick important thing to say is that we cannot patch Temper Monkey's source. That's not an option because it's signed, and it has special permissions. And Chrome blocks reloading modified versions with web requests blocking under manifest v3. And for this, you can actually use Brave, but in most cases, sticking to in-extension tricks is the safest way to stay under the radar. Okay, so now that's how you keep Temper Monkey under the radar, but Temper Monkey, as we've seen, is not fully automated, and at some point, you might need to scale up and collect more data or hit or pull updates at a higher frequency, and that's where headless and full browsers automation comes in, and I will leave it to François, who's going to present it for you.
Okay, so what are headless browser? So headless browser gives you the full environment of a real browser, just without the graphical interface. So no menu, no tabs, no windows. They make them lighter, faster, and ideal for automation scales. They use remote browser control protocol, like the Chrome DevTool protocol, also called CDP, or the W3C WebDriver protocol. So this is a W3C standard. And this are well supported in most popular programming language. So whether you are working in Python, in JavaScript, in Java or C#, you can drive a headless browser and automate pretty much anything you can do on a real one. So just to quickly explain how browser automation technology work as Puppeteer, Playwright, or Selenium, we typically have a script using one of these technologies. So these technologies are often a library or a framework. So Selenium is a framework, and Puppeteer is a library, Playwright is a library. So we have our script, and the browser automation technology send command to the browser engine through a remote control protocol. After the browser engine executes JavaScript through V8 or SpiderMonkey, parse the DOM, apply CSS, and simulate layout and rendering without a visible UI. So for our research, we focused on Selenium, and the Headless solution, the Headless browser automation technology that is again used today, and Puppeteer. So here is a list of remote control protocol used by a common browser automation technology. So we have the Chrome DevTool protocol. It uses HTTP and WebSocket. It is developed by Google. It's not a standard. However, it is bidirectional. That's why you use WebSocket. We have the WebDriver 2 standard of the W3C, sorry. It uses the HTTP protocol. We have Marionette, a custom Mozilla protocol that uses TCP for the transport. And to finish, we have the WebDriver BDI. So it's just a W3C draft, so not used today a lot because it's just a draft. But this is, they try to make the same thing as Google for the CDP. So to use WebSocket to make a bidirectional protocol. And for example, if you use Selenium with Chrome, you will use WebDriver 2 and partially the Chrome DevTool protocol. The communication is made indirect through the Chrome driver. So it's a binary available on the website of Google. If you use Selenium with the browser Firefox, you will use the protocol WebDriver 2 and Marionette. And the communication is made through the Gecko driver. And to finish, if you use Puppeteer, so a Chrome solution, Puppeteer is a JavaScript library developed by Google. So Firefox can be used with Puppeteer, but only at experimental stage. So personally, I never use Puppeteer with Firefox, only with Chrome. So Puppeteer uses directly the Chrome DevTool protocol. So here, we made a very high-level conceptual overview of a web browser and a machine network of a person who visit our website. The aim of this schema, is to identify multiple detection vectors to identify browser automation technology. So the use of a WebDriver, this kind of thing. So first, we have the JavaScript context. Everything accessible from the Windows object, like Web API, JavaScript function, HTML element attributes or properties. Second, we have the call stack, especially the stack trace, like TumperMonkey, explained just before. Third, we have the behavior on the page, so the navigation, click, and scrolling pattern. And finally, we have the private network, especially services exposed on the loopback interface. These are the key place where detection logic can catch automated browser in the act. So here are our 4 detections vectors. So we have the JavaScript context, the user behavior anomalies based on user input, the stack trace, which allow us to retrieve the call stack of hooked function, as previously explained with TumperMonkey. And finally, we have the internal network services exposure. So, in the JavaScript context of a page, there are a number of function property and element attributes that most bot detection solutions look at. For example, you have the botd project on GitHub developed by Fingerprint.js, so a subsidiary of the company Valve, the company who develops Steam. And I suppose that Fingerprint.js has been developed for the security of Steam. And the most famous of this property used by the anti-bot solution is the WebDriver property. So you can see it on the left, Web API Navigator .WebDriver. So this is a simple Boolean that returns true or false depending on whether the browser is being remotely controlled by a WebDriver. Because this detection vector is already very common and well documented, we are not going to spend time on it. Instead, our demonstration will focus on the three other detection vectors that are less obvious but just as effective. So we have the user behavior anomalies. The second detection vector is the user behavior anomalies, pattern and in interactions that simply don't match what a human will do. The list isn't exhaustive, but here are some clear examples. On the keyboard side, typing speed is a giveaway. Automation solutions like Puppeteer or Selenium fill input field way too fast, much faster than even the fastest human typist. For the mouse, the big one is click precision. This framework tends to click exactly in the center of element every single time. A human's aim just isn't that perfect. Then there is interaction with elements that aren't even visible yet, like clicking a button at the bottom of a web page without ever scrolling down. That's a dead giveaway that something non-human is driving the session. I personally believe that there is an opportunity here to build a bot detection framework based on anomaly in user behavior compared to the classic user journey. So maybe I think that bot detection solution need an integration with analytic solution because they can increase the rate of bot detection. So here a demonstration. So let's make this concrete. We have talked about how automation tools give themselves away through a natural typing, perfect click precision, and impossible interaction. Now I'm going to show you exactly what that tool like in practice. In all our demos, we use the same script. So for Puppeteer, for Selenium, this is exactly the same script. This is just a Python script for Selenium and a JavaScript script for Puppeteer. It fills two HTML elements, an input and a text area, and then it clicks on the image, so the leftmost image on the page. So here is how Puppeteer with Chrome performs that sequence. So here I just show you the JavaScript script. It just fills an input, a text area, and click on an image. So I run the script, so Puppeteer test. I just wait that the script fills the input. So as you can see, the input and text area element has been filled. The click is OK. And now, if you go on our detection dashboard, you can see click exactly on the center. So it's almost impossible for a human. And you have also typing too fast. So the solution type 20 Ks in 70 milliseconds. So 3 milliseconds per K. I made some tests. If I let, for example, the AK push on my browser, we cannot have the speed. Now, sorry. So now this is a demonstration with Selenium using the Firefox browser, so the Gecko driver. So I show you again the script, but this is the same just in Python. So I run the script. Oh, okay. Maybe I think we don't have enough time to show you all the demonstration, so I just go fast to the next slide. So for the stack trace inspection, so here is the common structure of a stack trace. So stack trace is just a representation of call stack. Sorry. So the stack trace is composed of the name of the call function, the file or URL where that function is located, the line number where the call occurred, and the exact position. So we found a very nice stack trace fingerprint, this one. So the ID highlight in red is the web element identifier that you could find in the W3C WebDriver specification. So if we found this ID in a stack trace, we are sure that there is a WebDriver that controls the browser. There is also other stack trace, but they are less good because this could be possible that it's false positive. It's false positive. Sorry. I don't have the necessary time to show you the stack trace inspection demo, but maybe I could just. I will skip that. I'm sorry, but if you want to check the video after, there is no problem. And to finish, the last detection vector is the internal network service exposure. So our research here focuses on the exposure of services on the private network and the local device. As we covered earlier, browser automation library use control protocol like the W3C WebDriver and the Chrome DevTool protocol. This protocol opens local listening services, and that exposures can be detected. So here, to give you a better idea of this slide, aim to illustrate, imagine that you want to create a tool similar to Nmap, so the network mapper, that runs from a web page in a browser to scan the internal network of a person visiting your website. So the diagram below shows a non-exhaustive list of methods for client-side service discoveries. So you can, for example, use exposed resources. If a web services expose JS, CSS, or images, you can just load this resource on our web page and show if they exist. So you can make service detection for HTTP services only. Because on the web aspect, the same origin policy don't concern the exposed resource. For the JavaScript, only the ES module, but not the JavaScript that are not module. So for our demonstration, we will use a WebSocket probing to perform a TCP port scan on the internal network of a person who visit our website. And after, you will use service discovery to determine if it's a CDP services. So there is two very interesting endpoints. The copy of the front end that shipped with Chrome, because there is a lack of content security policy, and there is a client-side, server-side request forgery. So you can trigger the client-side, server-side request forgery by adding an hidden iframe on our web page. So with this allows us to determine if the detected service is a Chrome DevTool protocol. And after, we have the JSON or JSON list endpoint that lists all open URL in the controlled browser, but also all iframe URL, including in the web page open. So with this URL, you can perform timing attack vector via dynamic iframe injection with very long URL. With this timing attack, I can determine if the CDP services that I have detected is this one that is used to control our browser. So here, I'm sorry because we lack of time, but this is our proof of concept. How work our proof of concept? Puppeteer and Selenium open CDP when you use Chrome, open the Chrome DevTool protocol services on an ephemeral port, so a random port. So the aim is to determine what is this ephemeral port, because it's complicated to scan the 65,000 port. So first, we get the initial source port, first by using an IPv6, because I made some tests, and when you use a network with an IPv4 that is shared across a lot of clients, the internet service provider perform port address translation. So we lose the real source port open on the client of a client's machine. After, we make estimate ephemeral port rate. So we just send 20 sequential fetch, and we just determine how many ephemeral ports are open by second on the web page, on the client machine, sorry. After, you just multiply this rate by 60, because if a CDP services is open on the machine, on the client machine, is before the initial source port. Why? Because en fait, we assume that if someone is visiting our website with a browser control via CDP services on an ephemeral port, this port will necessarily be before the source port reach through from the web page list. We start by estimating, and we also add some fixed port list. For example, the most port number used for CDP is 9222, because this is the default port specified in the Google documentation. So we'll just make you the demonstration of our POC. So first, I just start a Google with the remote debugging port. So when you run Google with the remote debugging port, it starts a CDP services. So I put the port 3332, sorry. So I'm sorry, because the port scan takes some time. So as you can see, we have detected the port 3332, but we don't know yet that it's a CDP, because you perform WebSocket probing to scan all TCP-based service on our localhost machine from the web page. And after, you have been determined that it's a CDP using our client-side, server-side request forgery. Here is some information returned by the DevTool frontend. But we are not sure that this is the CDP that controls our browser. And here, we will open a lot of iframe with very, very big URL to increase the content length of the response of the JSON endpoint. And after our timing attack, you can you know that this port is used to control our web page. And here, this is exactly the same, but we use the Selenium driverless. So Selenium driverless is a project on GitHub to have a stealth Selenium WebDriver. And I start the Selenium driverless script after I let open the previous port, so 3222, the remote debugging port of the previous video. So here, by using WebSocket probing to scan, we found two ports, so 2232, the previous one, and an ephemeral port. So the first is not the CDP service used to control the currently browser. And if we just wait some time, as you can see, we determine that the CDP services open on the port 35966 is the CDP service used to control our browser. I don't have the time to... This is exactly the same with Puppeteer. Okay. Okay, sorry. So here I just made the same with Puppeteer. So Puppeteer has Selenium open the CDP services on a random port, so ephemeral port. So I'll just let the script fill the input and text area HTML element and click. I don't speed up, I think, this video. So yes, we have the user behavior of Puppeteer, and we found the port 36786, so an ephemeral port, and this is the port, the port exposed the CDP services used by Puppeteer. So we also found the port 3332, because actually we have two CDP services open on our machine, as previously. And as you can see, the CDP services on the port 786 is the CDP services used to control our browser. So the browser open our website scrapme.fun. So here is a summary of our results. So the 3 detection vector we test. So if you use Puppeteer Extra, Selenium, or Selenium, the user behavior anomalies detection vector work for all of them. The user behaviors anomalies doesn't work for Selenium driverless because Selenium driverless has been designed to be stealth by design. After that, we have so for the stack trace inspection, it only really work for Selenium with Chrome, and to be more precise, with Chrome driver. This is the Chrome driver that leaks the web element identifier, unique identifier specified in the W3C documentation. For Firefox, it partially works, but you can increase the accuracy of the stack trace fingerprint by parsing the code before. Because you can parse the source code of our web page and check if our fingerprint is not a false positive due to an inline script on the web page. And to finish, our CDP scanner, so client-side CDP scanner, works for all solutions, even Selenium driverless when we use Chrome, because CDP is for Chrome. I wait that the W3C finish the WebDriver BDI to check if we can also perform this kind of scan. So, how to bypass our detection vector? So for JavaScript context, you have a lot of solution on GitHub. This is just to mock function. So you override function to return false data that simulate a real browser. So, for example, with Puppeteer, we have the Puppeteer Extra Plugin Stealth NPM package to make that. For the user behavior anomaly, you need to simulate a realistic user journey, so emulating human interaction flow. So, for example, when you fill an input, you need to see the input, to click on it, you need to generate onKup or onKdown event, etc. So you have a lot of tools for that. Selenium driverless made that natively. You have the NPM package Extra Humanize. You have also Puppeteer Extra plugin human typing to reduce to not generate too fast typing. For the stack trace inspection, avoid using automation methods that show up in stack trace, so just avoid to use the Chrome driver. This is my conclusion, because all solutions I test except Chrome driver are not fingerprintable using stack trace. And to finish, you have the internal network scan detection vector. So block access to services on private IP addresses and on the loopback interface from the browser. You can use iptable, AppArmor, EasyLinux, so some hardening tool. And for Windows, you can just use NetSH to configure firewall rules. And to finish, disable sequential ephemeral port allocation. To be honest, for the ephemeral port allocation, I only test on Windows, not Linux. So to disable sequential ephemeral port allocation, some solutions I think are use proxy to randomize port allocation or to randomize port allocation, or use an intermediate network hardware router or firewall to randomize port allocation. So, for example, you can perform port address translation with our router to hide the real source port open on our machine. So, I let Sukema explain.
Okay, so we're just going to break it down for you side by side so you know exactly when to use each method. So for us, TemperMonkey often slips past anti-bot systems, as we said earlier, because it runs inside a real browser and it has a user-driven browser profile and looks like a normal human browser, so it's hard to classify as a bot traffic, and it's generally ignored by anti-bot tools since it's seen as a personal automation and not a strapping engine. But the trade-off is it's not fully autonomous, so it needs some level of human interaction, which sometimes can be very useful for semi-automated tasks or assisted OSINT tasks. And on the other side, we've got the full browser automation, or the headless and headful browsers, sorry, which are Selenium, Puppeteer, and Playwright. They don't need a human in the loop, and they are ideal for high-frequency polling to capture rapidly changing data, and they can handle large scale. So they work across multiple languages, and they are perfect for big data or high-volume OSINT operations. But the trade-off here is quite the opposite. They are much easier detected for anti-bot systems, and you will need to do fingerprint evasion baked in from the start. So to make it simple for you, if you need to look human, you gotta go TemperMonkey, and if you need to move to a machine speed, go full automation. So thank you, everyone, and we'll be happy to take your questions.
Thank you. So I'm going to see, are there any questions from the internet? No. No one has been able to figure out how to ask questions from the internet. We've probably got time here if we go into the break for one or two questions, if anyone has any questions. Yes. You may have to yell.
Ça devra peut-être me traduire.
So for the headless browser, basically for the taking your correction, can you also do easy like scroll? Because some pages load with JavaScript view information. You don't have the next page.
Can you please give him the mic, because I was not able to hear anything. I'm sorry.
Oh yeah, sure, you can.
Yeah, you can come actually to the...
That way it makes sense to the recording.
Okay. So can you fake scrolling actually? So the JavaScript on the site loads more.
Can you fake scrolling?
Yes, you can fake scrolling.
Okay, thank you.
Yes.
That's
If you guys have any other questions, you can come to us at the Ninja Village.
We're going to have to call it there, but if you wish to corral Francois and Suhina, they'll be outside, and you can harass them with your questions as much as you want. Big round of applause, please. Thank you very much. Also, if you work for an AI company, forget everything you just saw, because all of that shit they will pay you handsomely for.